All right, so we eased into the chapter. Now we're ready to go in a little deeper into the concepts here in gases, and in particular, we're going to be looking at gas pressure. Now, I was a little glib in the last segment when we talked about gas pressure, and I said that that's the gases exerting their force against the walls of the container, and that's true for gas pressure, but pressure itself generically is a force per unit area. In the case of gases, it's the area of that container wall. But I did want to correct myself, because if we've got any physicists out there, I know how uptight you can be, and technically pressure is a force per unit area. When we talk about gas pressure, we're usually talking about the container as that area that the gas exerts its pressure against. So as we see here, gas pressure is the force acting on a specific area. So pressure, capital P, is equal to force per unit area. And therefore, we have a number of different combined units to give that. So ATM, or millimeters of mercury, or torr are common ones. Pound per inch squared is a very nice one, actually, aside from being that terrible English system that they don't use in England, that we seem to be the only place still using here in the United States. So I don't like the pound, I don't like the inch, but it is very nice because pounds are a unit of force, which is why weight is measured in pounds, whereas mass, it couldn't be in pounds, it's in kilograms. And then the area, inches squared, is an area, right? A distance times a distance is a square distance unit of inches squared. It gives an area. And then kilopascals. So the one that actually makes the most sense here is the one you'll see the least, pounds per square inch. But you may see that in tire pressure for automobiles, right? Usually it's abbreviated PSI, and that's an example in everyday life where you might see it. So ordinarily, tire pressure tends to be around 30 PSI above atmospheric pressure. So we see here that 1 atmosphere, which is our standard unit that we'll use in chemistry, we can see that's equal to exactly 760 millimeters of mercury. So that 1 and that 760, they're not considered to be sig fig limiters. Likewise, a torr in a millimeter of mercury, torr named for Torricelli, who discovered that unit, it would be exactly the same. However, 1 atmosphere is equal to 14.7 pounds per square inch, and that I would provide you if I ever were to ask any questions that go into PSI. And 1 atmosphere is also equal to 101.325 kilopascals. That's another relationship that I would give. So I'd probably even give you 1 atmosphere equals 760 millimeters of mercury, frankly, just to be fair. But I would expect you to know that 1 millimeter of mercury is equal to 1 torr, and therefore 760 millimeters of mercury equals 760 torr, rather. So not a whole lot of memorization here at all, but you should be able to work with these values if provided. All right, let's pause here briefly for a learning check, and we have actually 2 learning check questions. First of all, what is 475 millimeters of mercury expressed in atmospheres? And then second, the pressure in a tire is 2.00 atmospheres. What is this pressure in millimeters of mercury? So take a moment to answer each of those questions, and pause the video here while you do that work, and then start back up when you're ready, and we'll see how you did. All right, so there we have the first question. It actually ended up being B, 0.625 atmospheres. Again, if you just look by inspection, 475 is a little more than half of 760, so you know you're a little more than half an atmosphere. But if we want to do the math rigorously, we use our conversion factor, 1 atmosphere over 760 millimeters of mercury. That way we can cancel the units of millimeters of mercury, be left in units of atmosphere, and mathematically, when we take 475 divided by 760, we get 0.625. For the second question, if we take that 2 atmospheres and we multiply it by 760 millimeters of mercury per 1 atmosphere, we end up with choice B again, only this time the B is for 1520 millimeters of mercury. Okay, so hopefully that was pretty simple and just got you started on this idea of using conversion factors to determine one resulting type of pressure unit when you're starting in a different pressure unit. Now, it's easy to forget that we live at the bottom of a sea of air. We have a significant atmospheric pressure acting on us at all times, And it does change, and that's when we notice it, when we get these low pressure systems or high pressure systems moving through fairly rapidly. We notice things, we get wind, and then it's noticeable. But for the most part, on a nice calm day, we can forget all about that atmospheric pressure that's there. So be careful. Gases in particular get overlooked sometimes because they're often odorless and colorless and invisible, and so we don't think about them, but they're a very important part of our world. If we want to put a number on that, the atmospheric pressure, that pressure exerted by the column of air on top of us, at sea level, it tends to be a roughly 1.0 atmosphere. That's why the atmosphere is such a popular unit in gas laws. If you go up in distance, then you don't have quite so much air pressure. The atmospheric pressure drops if you're on the top of a high mountain, let's say, and so your pressure might be something like 0.70 atmospheres as opposed to the sea level value of roughly 1 atmosphere. So summarizing that, atmospheric pressure is about 1 atmosphere at sea level. Again, conditions do change. We get hurricanes and other weather events, but by and large, the average atmospheric pressure is roughly 1 atmosphere at sea level. It is dependent on altitude and the weather. It's lower at higher altitudes where the density of air is less, and it's higher on a rainy day than on a sunny day. So you do have to take all those things into account. If you have ever lived in a high altitude location, or you've ever thoroughly read the box of cake mix that you may have purchased, you'll see that there are high altitude directions for doing things like baking cakes because the atmospheric pressure is less. The boiling point of water is actually less, and so therefore you have to cook it a little longer because the water doesn't boil at quite as high a temperature. So there are real world consequences to all of this stuff, dealing with these invisible, colorless, odorless gases. But again, it does have real world complications, and we do have to at least try to understand these invisible aspects of our daily life a little better if we want to have a fuller idea of science. So table 7.3 gives some altitude and atmospheric pressure average values. So we see when you're very low, like in the Dead Sea, which is actually below sea level, you're even at a higher pressure than atmospheric pressure, roughly 800 millimeters of mercury as opposed to 760 at sea level. Los Angeles, pretty much at sea level, maybe just a little above and therefore a little lower, 750. Las Vegas, Nevada, they're up in the mountains a bit, so now we're down to 700 millimeters of mercury for the atmospheric pressure. Denver, higher yet, therefore now a lower atmospheric pressure. And finally, as we look at really high altitudes like Mount Whitney and then finally Mount Everest, atmospheric pressure at the top of Mount Everest, a mere 250 millimeters of mercury. That's a problem because our lungs are really built for about 760 millimeters of mercury, so it's tough to extract the oxygen at that low pressure. And unfortunately, a number of people every year will try to climb Mount Everest and unfortunately not make it for one reason or another because the body's just not built for those sorts of conditions. So if this atmospheric pressure is so important, then how do we measure it? Well, the answer is we use a barometer, and a barometer measures the pressure exerted by the gases in the atmosphere by the height of mercury in the column. Mercury is a toxic gas and a toxic liquid and gives rise to toxic compounds. So it's not our ideal choice, but we use mercury because it's a very dense liquid and it will respond well to these pressure changes. Unfortunately, there does have to be some contact of the atmospheric gases with the mercury, and therefore some ability of the mercury to escape the barometer, but we've done a very good job in designing barometers nowadays that minimize any exposures to the mercury. So they're quite good. There are also other possibilities. You could use a water-based barometer. It just has to be about 3 stories high as opposed to the standard mercury barometer, which is just a foot or so high based on those density differences between mercury and liquid water. So again, they're useful, and there are other ways, pressure-sensitive probes nowadays, but the classic measure and still often used, the old mercury barometer, does a very nice job of measuring gas pressure. All right, so let's end this section of the chapter with a final learning check. And this learning check, like the other one in this section, will have two questions. So first, the downward pressure of the mercury in a barometer is blank the pressure of the atmosphere. So make your selection there. Hopefully that one's nice and simple. And then number two might take a little longer because it says a water barometer is 13.6 times taller than a mercury barometer, based on that density difference of water having a density of 1.00 grams per milliliter and mercury being about 13.6 grams per milliliter for its density. So why is that? And you'll make those answer choices as well. So pause the video if you need. If you've already made your selections, then just listen and we'll see how you did. All right, so for number one, it's the same as the pressure of the atmosphere. That's why we can use that mercury barometer, because it gives us the downward pressure of the mercury in the barometer is equal to the pressure of the atmosphere, and we can read that value off very nicely. And in the second example, the reason why those water-based barometers are quite tall, so again, a couple stories as opposed to a foot or two tall mercury barometer, is due to water is less dense than mercury, a lot less dense. Than mercury is 13.6 times more dense than water. So hopefully this section on gas pressure was just as nice and friendly as the beginning section on gas properties, and you'll be eager to move on to the next section. If not, you're certainly welcome to contact me if you're having any troubles or need any clarification. But otherwise, I'll see you in the next section.